If we look up at the night sky, the first thing we see is a quiet black background, as if the universe was simply a vast emptiness where stars sparkle. In many people's imagination, space is nothing more than nothing at all, an empty region where planets drift and galaxies silently spin. But the more we learn, the more we realize that this seemingly meaningless void is actually one of the strangest and most dynamic parts of the universe. For many centuries, scientists thought something similar. In Isaac Newton's classical view, space was like a great stage. Everything happened upon it. Planets moved, stars shone, while space itself remained motionless, flat, and unchanging. Time flowed steadily like a cosmic clock, and space was simply a three-dimensional coordinate system that kept everything in its proper place. Then, Albert Einstein came along and completely transformed that picture. In his view, space is not a silent backdrop. Instead, it is more like a gigantic fabric that can bend, twist, and stretch. When combined with time, it forms a four-dimensional structure called space-time. And this structure is not merely a passive arena. It responds to the mass and energy that exist within it. A helpful way to imagine this is to think of a stretched rubber sheet. If you place a bowling ball in the middle, the surface dips downward. When a marble rolls across the sheet, its path is no longer straight, it curves around the indentation. In Einstein's universe, stars and planets play the role of that bowling ball. They bend the space-time around them. That curvature is what we perceive as gravity. We fall toward Earth, not because the planet pulls us like a magnet, but because the space-time around it has been curved. Yet the story does not end there. Even far from every star, deep in the darkness between galaxies where it seems nothing exists, space is not truly empty. On scales smaller than atoms, quantum physics reveals that space is filled with invisible quantum fields. Every type of particle in the universe is associated with its own field. Electrons arise from the electron field, photons from the electromagnetic field. What is fascinating is that even when no particles are present, these fields never remain completely still. They constantly fluctuate, like the surface of a lake that appears calm from afar but reveals tiny ripples up close. These fluctuations can briefly create pairs of particles that appear and vanish almost instantly, like fireflies flickering in the night. Physicists call them virtual particles, and the energy behind these fluctuations is known as vacuum energy. We cannot directly see these fleeting particles, but their effects can be measured. They influence how electrons move around atomic nuclei, and may even be connected to an even deeper mystery, dark energy, the phenomenon that appears to be causing the universe to expand faster and faster. So the space that appears empty to our eyes is actually full of hidden activity. Space is not an empty box in which the universe places its stars. It is a dynamic structure, constantly fluctuating and evolving. And perhaps most strangely of all, that structure itself can expand not simply because galaxies are flying away from one another, but because the very space between them is quietly stretching. That idea has become one of the foundations of how we understand the universe today. If you stand on a quiet hill on a clear night and look up at the sky, the first feeling is often one of infinity. The universe stretches out in every direction, seemingly without end, without boundary. But in reality, there is a very real limit, not the place where the universe ends, but the point where our ability to observe it stops. That limit is called the observable universe. It includes every signal that has had time to reach us since the dawn of time. Light from distant galaxies, ancient radiation, and even gravitational waves traveling through space. Beyond that boundary does not mean nothing exists. It simply means that light from those farther regions has not yet had enough time to reach Earth. If we follow our intuition, we might guess that this boundary lies about 13.8 billion light-years away, corresponding to the age of the universe. But the universe is not quite that simple. During the time that light has been traveling toward us, the space between galaxies has been continuously expanding. As a result, the galaxies that emitted that light billions of years ago are now much farther away than where they originally were. Today, cosmologists estimate that the radius of the observable universe is about 46.5 billion light-years, meaning the entire cosmic bubble around us is nearly 93 billion light-years across. To picture this, imagine a loaf of bread rising in the oven. The raisins scattered throughout the dough are like galaxies. As the bread expands, the distance between the raisins increases. If a beam of light leaves one raisin just as the dough begins to rise, the dough continues expanding during the entire journey of that light. Its destination keeps moving farther away even as the light travels toward it. From this expansion comes the concept of the cosmic horizon. It is not a wall at the edge of space, nor a place where a spaceship might crash into something like in a cartoon. It is simply a boundary of information, the distance beyond which light is still on its way and has not yet reached us. You might imagine it like standing in the middle of a thick fog. Nearby lights are visible, while farther ones fade into a hazy distance that has not yet come into view. Over time, as ancient light continues to arrive, that fog slowly recedes. The cosmic bubble around us gradually grows larger. But even before thinking about such enormous boundaries, it is worth pausing to remember that space itself, the thing that seems most empty, contains far more than we once imagined. On microscopic scales, the vacuum is not silent. It fluctuates, trembling gently like the soft crackling of a distant fireplace or the faint rustle of leaves in a quiet night. These fluctuations reveal that space is not simply the absence of matter. It is a real physical entity that can bend, expand, ripple, carry energy, and even possess temperature. Even the deep emptiness between galaxies is still a few degrees warmer than absolute zero, thanks to the faint leftover glow from the moment the universe was born in the Big Bang. So when we ask, what is space? The answer is no longer just an empty void. It is a complex fabric that connects everything in the universe, from the tiniest atoms to the largest galaxies. Space is not merely where the story of the universe takes place. It is part of the story itself. And the more scientists study it, the more they realize that space seems almost determined to refuse being empty. It fluctuates, stretches, twists, and occasionally surprises us in fascinating ways. As for those mysteriously missing socks, space probably isn't responsible. But if one really did slip into a fold of space-time, then at least it would have become part of a rather unusual scientific mystery. There is a rather strange truth about the universe. A part of it is gradually slipping beyond our reach. Not because galaxies are breaking the speed limit of light, but because the space between us and them is expanding too quickly. So quickly that the light they emit from this moment onward will never reach Earth. Not in billions, or even trillions, of years. In a very real sense, a portion of the universe is quietly drifting out of humanity's view. And yet there is still something astonishing to pause and appreciate. Everything we see in the night sky, every star, every faint smear of distant galaxies, lies within our cosmic bubble of visibility. This is the observable universe, a vast region of space about 93 billion light-years across, containing nearly 2 trillion galaxies, each one home to anywhere from millions to trillions of stars. The light from those distant galaxies has traveled through space for billions of years just to end its journey on your retina or on the sensitive surface of a telescope. Some of the photons reaching our eyes tonight began their journey before Earth even existed. They are like ancient messages drifting through the cosmos, finally finding their recipient after billions of years of silent travel. And yet, all of that richness may still be only a small slice of the true picture. Beyond the cosmic horizon, space may continue forever. It might be flat, curved, or even folded into strange geometries we have never imagined. But if light from those regions can never reach us, we may never know for certain. What's fascinating is that every location in the universe has its own observable bubble. If an astronomer stood on a galaxy 10 billion light-years away, the portion of the universe they could see would overlap with ours only slightly. The rest of their observable universe might include regions humanity will never witness. So the observable universe is not the whole universe. It is simply our piece of it, And that peace alone is enough to overwhelm the imagination. Because when we look up at the sky, we are not really seeing the universe as it is now. We are looking into the past. Light takes time to travel. A light year, the familiar unit used by astronomers, is the distance light travels in 1 year, nearly 10 trillion kilometers. If a star lies 100 light-years away, the light we see from it tonight actually left that star a century ago, when our great-grandparents were still young. As the distances stretch to billions of light-years, the time we look back into the past grows just as vast. There are galaxies whose light began its journey before the solar system formed, before Earth had oceans, even before the first life appeared. Astronomers call this interval look-back time, the time we are looking back into cosmic history. In this sense, the night sky is like a vast archive of the universe's past. The galaxies we observe may have changed completely since the moment their light began traveling toward us. Some may have collided and merged with other galaxies. Some may have stopped forming stars. And some have drifted so far away that any new light they emit will never reach us again. During its long journey through an expanding universe, light itself is stretched along the way. Its wavelength grows longer, shifting toward the red end of the spectrum, a phenomenon astronomers call redshift. By measuring this shift, scientists can determine how far away a galaxy is and how long its light has been traveling before reaching us. Each photon therefore acts like an ancient messenger, carrying subtle clues about where it came from and about the state of the universe at that time. From these tiny messages, humanity slowly pieces together the larger picture: how fast the universe is expanding, how galaxies evolve, and how dark energy may be quietly shaping everything. To collect these messages, we build telescopes, true time machines. A small telescope in your backyard can show you Jupiter as it existed about 40 minutes ago. Larger observatories reveal galaxies as they appeared hundreds of millions of years in the past. And then there are giants like Hubble and James Webb, artificial eyes capable of looking so deep into space that they capture the light of the first galaxies that formed only a few 100 million years after the Big Bang. It is a strange irony. To understand the future of the universe, we spend most of our time looking into its past, because light, no matter how fast it travels, still needs time to cross the immense distances of space. This means the universe we experience is always slightly out of date compared to reality. It is like watching an enormous film assembled from scenes recorded at different times, some from nearby galaxies, others from the deepest reaches of space. But that delay is also a precious gift. Because of it, we can see many different chapters of cosmic history at once. The night sky becomes a patchwork of time. In one direction, a young galaxy relatively close to us. In another, the faint glow from an era when the first stars were just beginning to form. In a way, we are living inside a vast museum, built entirely of light. It is strange to think that the night sky does not simply come to us. Instead, tiny photons have traveled across immense distances for billions of years to tell their story. They quietly cross expanses that the imagination can hardly grasp, only to finally touch the eyes of an observer. And in that moment, we realize something beautiful. Every time we look up at the sky, we are looking into a natural time machine. The light that has just reached your retina may have left its star before trees appeared on Earth, before the first living cells formed, or even before our planet's atmosphere began to breathe. Much of what we know about the universe comes from listening to that light. By studying subtle changes in its color, its shift, and its age, scientists have learned how to decode a silent language written over billions of years, a language that does not merely describe the universe, but in a sense is the universe, encoded in the motion and memory of light. So when a star flickers overhead, what we are seeing is not its present. It is a version preserved in time, a fragment of history still racing through the darkness to reach us. Each point of light in the sky is like an old page from the story of the cosmos, and science patiently pieces them together, one distant beam at a time. To understand the limits of this observation, imagine an early morning in a quiet field. A layer of fog spreads gently across the ground. You can see a few tree trunks, a distant hill, but just a little farther away, everything fades into a pale blur. You know the world continues beyond the mist, your eyes simply cannot reach it yet. Living in the universe is much the same. No matter how powerful our telescopes become, our view will always have limits. Not because of fog, but because of three fundamental factors: time, distance, and the expansion of space. Cosmologists collectively call these limits cosmic horizons. The first of these is the particle horizon, the greatest distance from which light or any signal could have reached us since the universe began. Because the universe has existed for about 13.8 billion years, and space has expanded throughout that time, this boundary today lies as about 46 billion light-years away in every direction. This forms an observable bubble, roughly 93 billion light-years across the entire region of the universe humanity can currently detect. But this horizon is not a wall at the edge of the universe. There is no line in space that says "stop here." It is simply the limit imposed by how far light has had time to travel. Like standing on a beach and looking out at the ocean, you can only see as far as light allows, not because the sea ends there, but because your vision stops at the curve of the horizon. Beyond this lies another concept, the cosmic event horizon. Unlike the one surrounding a black hole, here it refers to the boundary beyond which events will never be able to influence us in the future. Regions of space beyond this limit are receding so quickly that any light they emit will never catch up with us. Imagine sending a message in a bottle to a friend drifting away on a raft in a strong river current. You toss the bottle into the water, but the current carries the raft away faster than the bottle can reach it. The letter will never be delivered. In the universe, the event horizon works in a similar way. Today, this boundary is estimated to lie about 16 billion light-years away. That means there are galaxies we can still see today, but if they emitted new light at this very moment, that light would never reach Earth. We are witnessing galaxies that are slowly slipping beyond our ability to communicate with them. There is also a broader concept called the cosmological horizon, used to describe observational limits created by the very structure of space-time itself. It reminds us that these horizons are not merely visual boundaries, but direct consequences of the physics of the universe. Interestingly, these horizons are not fixed. As time passes, the particle horizon expands, because more and more ancient light has time to reach us. But at the same time, because dark energy is causing the universe to expand faster and faster, more galaxies drift beyond our ability to interact with them. The universe therefore becomes larger, yet more isolated. Perhaps the easiest way to imagine this is to picture a balloon being inflated. Small dots drawn on its surface represent galaxies. As the balloon expands, the dots move farther apart, and the ones farther away recede faster. We can only see the dots close enough for their light to cross the ever-growing distance. Farther away, the light becomes stretched, dimmer, and eventually disappears into the expanding darkness of space. There is something both somber and gentle in knowing that our vision has limits. Even though the window through which we observe the universe is vast beyond imagination, it is still only a finite frame. What we see depends on the history of light, how long it has traveled, what expanses it has crossed, and how space-time has changed along the way. This means that there will always be regions of the universe beyond our understanding, not because humanity lacks technology or intelligence, but because the very structure of space-time sets the boundary. These regions are not hidden behind a curtain waiting to be lifted. They lie beyond the reach of information, where no signal can ever cross to tell us what is happening there. And yet, what is remarkable is how much humanity has learned from this finite portion of the universe. We have mapped galaxies, measured the faint background radiation left from the early universe, and traced the ancient fingerprints of the Big Bang. Cosmic horizons do not confine our imagination. Rather, they are like the frame of a painting, shaping how we see the grand picture of the cosmos. Each new discovery is like the morning sun slowly lifting the mist. Our view expands a little further, and the cosmic landscape becomes clearer. Still, far beyond lies regions hidden behind the curve of expanding space, places whose light will never reach us. And here we are, on a small corner of the universe, quietly spinning with the Earth, observing photons that have traveled billions of years to arrive. We read those ancient messages and wonder what awaits beyond the next bend in the cosmic road. Even if we never see the entire picture, the beauty lies in the effort to understand. In listening to the whispers of light and following them to the edge of knowledge, we realize that we ourselves are part of that story. In truth, humans did not always think the universe was changing. Not long ago in the timeline of science, many believed the universe was a quiet, static stage, galaxies resting in place, stars burning steadily, and everything existing in a nearly eternal balance. Then, in the early 20th century, from an observatory high on a mountain, a discovery quietly changed everything. Edwin Hubble noticed that light from distant galaxies was shifted toward the red end of the spectrum. That meant they were moving away from us. And even more interestingly, the farther a galaxy was, the faster it appeared to recede. This was not a random coincidence. It was a law. The universe is expanding. But this expansion is not like galaxies racing through empty space like cosmic cars. What is happening is far more subtle. Space itself is expanding. Imagine a loaf of raisin bread rising in the oven. The raisins scattered throughout the dough are like galaxies in the universe. As the dough expands, the distance between the raisins increases, not because the raisins are moving on their own, but because the dough between them is stretching. The universe behaves in much the same way. No galaxy sits at the center of the expansion. From wherever you stand, all other galaxies appear to be moving away. This leads to a rather strange conclusion. The universe is not expanding into some external space. It is simply expanding. The distances between objects that are not gravitationally bound grow larger over time, as if the ruler of the universe itself were slowly stretching. At first, this idea puzzled many scientists, even Albert Einstein. When he developed general relativity, he added a term to his equations called the cosmological constant in order to keep the universe static. After learning of Hubble's discovery, Einstein reportedly called this decision the greatest blunder of his life. Ironically, that very concept later returned in modern physics to help explain dark energy. Perhaps the most beautiful consequence of discovering that the universe is expanding is this. If galaxies today are moving farther apart, then in the past they must have been much closer together. That thought led scientists to a bold idea that the universe once began in an extremely hot and dense state. We call that moment the Big Bang. The name sometimes makes people imagine a gigantic explosion in space, like fireworks in the night sky. But the reality is quite different. There was no center, no radius of explosion. Instead, all of space everywhere at once began expanding from an incredibly dense and hot state. If someone asks where the Big Bang happened in the sky, the answer is actually quite surprising. There is no particular direction at all. There is no point in the universe you can point to and say, it began there. The Big Bang happened everywhere at once, even at the very place where you are sitting right now. And that beginning has not truly ended. After nearly 14 billion years, the universe continues to expand. Galaxies quietly drift farther apart, and their light is gradually stretched as it travels through expanding space. The farther we look, the more clearly this stretching appears. Light from distant galaxies is shifted toward the red end of the spectrum, as though space and time themselves are being stretched along with it. Yet this strange expansion does not affect everything around us. Your morning cup of coffee does not drift away from your hand. The atoms in your chair remain tightly bound together, and our Milky Way galaxy still holds its structure. On smaller scales, gravity and the other fundamental forces are strong enough to keep things stable. But when we look on cosmic scales, the distances between galaxies and clusters of galaxies, the story changes. There, space continues to stretch. And in the late 1990s, astronomers discovered something even more surprising. This expansion is not slowing down as expected. It is accelerating. The phenomenon believed to drive this is called dark energy. We still do not know exactly what it is. It might be an inherent property of space itself, or a kind of physical field that science has yet to fully understand. But today, It appears to make up most of the universe's total energy budget, pushing galaxies farther and farther apart. There is a quiet beauty in this story. The universe began in an extremely hot and dense state, where everything was almost fused together. Over time it cooled, forming stars, planets, and eventually the conditions for life. And even today, that expansion continues slowly but relentlessly, like a story that began with a brilliant explosion and then unfolded into a long and endless chapter. In space there is no sound, but if there were, it might resemble the gentle rising of dough in an oven, a sound so soft it is almost impossible to hear, merely the subtle shifting of a universe that continues to grow. When we say the universe is expanding, we do not imagine galaxies flying outward from a central point. What is actually changing is the underlying fabric of reality itself, the structure of space slowly stretching, like a loaf of bread swelling in the oven. And we, together with this small Earth, are drifting along in that process. Every breath, every heartbeat, every human thought takes place on a planet spinning within this expanding cosmic dough. In physics, there is a rule that seems almost unbreakable. Nothing can move faster than light. According to Einstein's theory of relativity, the speed of light, about 299 million meters per second, is the ultimate limit for anything with mass. Yet when astronomers observe distant galaxies, they see something that appears to contradict this rule. Some galaxies seem to be moving away from us faster than the speed of light. At first glance, this might sound like physics has run into trouble, but in reality, no law has been broken. The secret lies in the fact that galaxies are not flying through space. Instead, they are being carried along as space itself expands. Imagine the surface of a rubber sheet dotted with many small marks. When the sheet is stretched, the marks move farther apart, not because they are moving on their own, but because the surface beneath them is expanding. If the stretching happens quickly enough, the distance between two marks can increase faster than light could travel across it. Yet the marks themselves remain still on the surface. The same thing happens with galaxies. Another way to picture it is like trying to walk forward on a treadmill that is accelerating backward. You continue walking normally, but the ground beneath your feet slides away even faster. As a result, the distance between you and the person ahead of you still increases. In the universe, light encounters a similar situation. It tries to travel across expanding space, but in extremely distant regions, space expands so quickly that light cannot make progress toward us. Relativity does not forbid space itself from expanding faster than light. It only forbids objects from moving through space at such speeds. In fact, shortly after the Big Bang, the universe went through an even more extreme phase known as cosmic inflation. In a moment so brief it is almost impossible to imagine, less than a trillionth of a second, space expanded at a rate far faster than light. During that incredibly short time, the universe grew from smaller than a proton to roughly the size of a grapefruit, or even larger. Once again, no physical laws were violated. Particles were not racing faster than light. Space itself was simply swelling outward. There is a remarkable moment in the history of the universe when the familiar rules of intuition seem to turn upside down. In the very early moments after the Big Bang, space went through a process known as cosmic inflation, an expansion so violent that it proceeded faster than the speed of light. It was not that particles were racing away at extraordinary speeds. Rather, space itself was swelling at a pace almost beyond imagination. This brief burst of expansion acted like a gigantic cosmic iron. It smoothed out the early wrinkles of the universe, stretching tiny differences so widely that the universe today appears almost uniform in every direction. When we peer deep into space, that strange balance is still visible, a lingering trace of the moment when the universe expanded so rapidly that even light could scarcely keep up. Billions of years later, this expansion has still not stopped. Space continues to grow, quietly pulling galaxies farther apart. And at extremely large distances, this stretching becomes so strong that some galaxies appear to be moving away from us faster than the speed of light. But that does not mean physics is breaking down. Those galaxies are not fleeing through the universe. It is simply that the road between us and them is stretching faster than light can cross it. Imagine trying to send a postcard across a river, while the opposite bank is drifting farther away with a powerful current. You might throw the card with all your strength, attach as many stamps as you like, yet the distance keeps increasing faster than the postcard can travel. Eventually, sending the letter becomes pointless. The universe works in a similar way. There are galaxies whose newly emitted light will never reach us. Strangely enough, we can still see some of those galaxies today. The reason is simple. The light they emitted long ago is still on its way here, but the light they are emitting right now has already moved beyond our reach. It is a little like watching the taillights of a car just as it turns a corner. The light remains visible for a few final seconds, but the car itself has already disappeared down another street. This gives the universe a beauty tinged with quiet melancholy. Out there exist countless stars and galaxies we will never know, not because we fail to observe carefully, but because the universe itself has drawn its stage farther away from our view. And yet, what humanity has already seen is astonishing. From a small planet orbiting an ordinary star, we have looked billions of light years in every direction. We have captured ancient photons crossing space, traced the formation of galaxies, and detected the faint afterglow left behind by the Big Bang. In a universe where space itself can expand faster than light, it is truly remarkable that a small species like ours can read these ancient stories written in light. When people think about the universe, many imagine it as a gigantic box, a dark void with clear edges, with an up and down, a left and right, as if it were floating inside some larger emptiness. Perhaps it has boundaries, perhaps it stretches forever, but the true shape of space is far more subtle. Space may not be flat like a tabletop. It can be curved, and that curvature can take different forms: positive curvature, negative curvature, or something extremely close to perfectly flat. The geometry of the universe is not merely a mathematical detail. It determines how the universe evolves, how light travels, and even the ultimate fate of everything that exists. One possibility is that the universe is flat. In this model, space is like a vast plane, extending infinitely in every direction. The familiar rules of geometry still apply. Parallel lines never meet. The angles of a triangle always add up to 180 degrees. And if you travel in a straight line forever, you will never return to where you started. But there is another possibility. In a closed universe, space curves back on itself like the surface of a sphere, or more precisely, the three-dimensional equivalent of one. In such a universe, if you could travel straight in one direction long enough and avoid every star and galaxy along the way, you might eventually return to the very place you began, as though you had completed a vast circle around the cosmos. If you walk in a straight line across the surface of the Earth, you will never fall off the edge of the planet. Instead, you simply keep walking, circling the globe, until one day you return to the exact place where you started, of course, after a journey so long that your shoes would need to be extraordinarily durable. This idea helps us imagine one possible nature of the universe. Space itself may curve back onto itself. But that is not the only possibility. Beyond a universe that is flat or curved like a sphere, there is another scenario, an open universe. In this geometry, space curves outward like a saddle or the surface of a Pringle chip. Parallel lines gradually drift apart. Triangles have angles that add up to less than 180 degrees. And if you begin a perfectly straight journey through the universe, you would never return to your starting point. The path would extend forever into the vast emptiness. These three shapes, flat, closed, and open, are not merely mathematical thought experiments. They are deeply connected to the amount of matter and energy that exists in the universe. Cosmologists call the dividing threshold the critical density. If the universe contains more matter than this threshold, space curves inward and forms a closed universe. If it contains less, space curves outward into an open universe. And if everything balances just right, the geometry becomes flat, a nearly perfect state, like the Goldilocks story of cosmology. Not too much, not too little, but just right. Interestingly, the universe has left clues for us. the ancient light of the cosmic microwave background, emitted shortly after the Big Bang, still drifts through space today. Tiny fluctuations in this faint glow allow scientists to measure how space bends the paths of light. From this, they can infer the geometry of the entire universe. And the result is astonishing. All current data suggests that the universe is almost perfectly flat. Not absolutely perfect, but flat enough that any curvature is too small for our current instruments to detect. Yet even a flat universe is not simple. It could extend infinitely, or it might be finite in a very subtle way. That might sound contradictory, but consider the surface of a sphere. Its area is finite, yet you will never find an edge. You can travel across that surface forever without falling off, because the entire surface connects back onto itself. Cosmologists think three-dimensional space might behave in a similar way, finite, yet without boundaries. A closed structure where no edge exists, only gentle curves that eventually return to themselves. And if we lived inside such a structure, we would almost certainly never notice it directly. We would simply keep moving forward, believing we are traveling straight, while quietly following the curvature of the universe. If the universe is truly infinite, the story becomes even stranger. An endless space could contain countless galaxies, countless stars, and perhaps even repeating structures. Somewhere unimaginably far away, there might exist another planet, another version of you, sitting and listening to this very story, perhaps differing only in a tiny detail, like wearing slightly different pajamas. Of course, all such speculation is limited by what we can observe. The observable universe is only a small fragment of the whole picture. Beyond that cosmic horizon, the true shape of space remains uncertain. Its curvature might be so subtle that even light traveling for billions of years cannot fully reveal it. It is a bit like standing in the middle of a vast field. You cannot see the curvature of the earth beneath your feet. Yet that does not mean the curve is not there. The geometry of the universe also determines its future. If space curves inward, gravity might one day win, pulling everything back together in a scenario known as the Big Crunch. On the other hand, if the universe is flat or open, expansion may continue forever, with galaxies drifting farther apart, and the cosmos gradually growing colder and darker with time. With the presence of dark energy, the Big Crunch now seems less likely. Instead, the universe appears to be heading toward a future where distances grow ever larger and light becomes increasingly rare. Whatever the true shape of the universe, flat like an endless plane, curved like a gigantic sphere, or open like a saddle, we are part of it. The atoms in our bodies obey the same geometry. The light we see traces the curves of space, and our thoughts themselves unfold within this cosmic structure. We do not simply live in space. In a sense, we are space becoming aware of itself. So whether the universe is curved, flat, or open, the most important thing is not finding the final answer immediately. It is enough to look up at the night sky, smile at the distant stars, and know that beneath our feet lies a tiny piece of a structure that is vast, strange, and wonderfully mysterious. Imagine that you are a tiny creature living on the surface of a balloon. Your world has only 2 dimensions. You can travel north, south, east, or west along the curved skin of the balloon. You cannot dig beneath it, nor can you fly above it. Your entire universe is just that surface, smooth, continuous, and closed. You have no idea that the balloon might be held by some enormous being outside it. From your point of view, everything is simply the surface. And if you keep walking straight ahead without ever changing direction, eventually you will return to the very place where you started. That is the strange nature of curved space. Its rules sometimes feel unfamiliar compared to our everyday intuition. Yet once we grow accustomed to its rhythm, everything begins to make a surprising kind of sense. By thinking about curved 2-dimensional surfaces like this, scientists can imagine how the 3-dimensional space of our universe might behave on the largest scales. On a familiar flat surface like a sheet of paper or the top of a table, geometry behaves politely. A triangle always has angles that add up to 180 degrees. 2 parallel lines will never meet. and if you walk in a straight line forever, you will keep moving in that direction, unless you encounter a wall, or perhaps a cup of coffee that someone has just spilled. But move onto the surface of a sphere, like our planet or that imagined balloon, geometry begins to behave differently. If you draw a triangle using great circles such as the equator and lines of longitude, the sum of its angles can exceed 180 degrees. Lines that appear parallel may gradually converge at the poles, or drift apart depending on how they are drawn. And the most intriguing part, if you travel straight across that curved surface, you can return to your starting point without ever turning. There is no edge, no boundary, only a continuous loop. From the perspective of the creature living on that surface, the world seems infinite, yet in reality it is finite, curved back onto itself. Now expand that idea. Imagine that our entire universe is like a three-dimensional version of that balloon's surface. Space does not curve in 2 dimensions like the balloon's skin, but in a more complex way within 3 dimensions, perhaps even within higher dimensions that our imagination struggles to picture. We live inside that space, moving through it without ever seeing the outside, just as the creature on the balloon can never see the air surrounding it. In this analogy, galaxies are like small dots drawn on the balloon's surface. As the balloon inflates, the dots drift farther apart, not because they crawl across the surface, but because the surface itself is stretching. That is exactly what cosmologists mean when they say the universe is expanding. If space truly is curved and finite, then in theory, a straight journey long enough could bring you back to where you began. There would be no edge of the universe to fall off, no boundary where space ends, only a vast curve perfectly closing back on itself. The balloon analogy also reveals another remarkable idea. The universe has no special center. On the surface of a balloon, no point is the center of expansion. When the balloon inflates, every point moves away from every other point. No matter where you stand and look around, everything appears to be receding from you in all directions. Of course, this analogy is only a simplified model to help our 3-dimensional brains grasp a deeper concept. The balloon's surface exists within a 3-dimensional space that we can see. But if our universe is curved, it may curve in a way that does not require any larger space around it at all. Space can curve simply because of its own structure. This is called intrinsic curvature, one of the most profound ideas in Einstein's theory of general relativity. According to that theory, space-time is not a fixed stage. It has shape, it has structure, and that shape can change over time. Mass and energy bend space-time, and the curvature of space-time guides how matter moves. A beautifully circular relationship. Matter tells space how to curve, and curved space tells matter how to move. It is this delicate dance that governs everything from the orbits of planets around stars to the motion of distant galaxies across the vast universe. Curved space does not only affect how galaxies move, it also shapes the paths that light takes through the universe. In a curved space, light does not truly travel in straight lines the way we often imagine. Instead, it follows special routes known as geodesics, the shortest possible paths allowed by the geometry of that space. On the surface of a sphere, geodesics are the great circles, like the equator. In the real universe, the path of light bends according to the structure of space-time and the gravity of massive objects. When light passes near stars or black holes, it can be bent, magnified, or even split into multiple images. This phenomenon is known as gravitational lensing. So when we look up at the night sky, we are not simply seeing points of light scattered across a calm, flat emptiness. We are looking at a web of light winding its way through curved space, stretched, bent, and shaped by the mass of everything that exists around it. The sky becomes a kind of slow-moving cosmic mirror, where tiny distortions reveal the true structure of the universe. Let us return to the image of the balloon once again. As the balloon inflates, the distance between the dots drawn on its surface gradually increases, but the dots themselves do not grow larger. The same is true for galaxies. They are not stretched when the universe expands. Systems bound together by gravity, like the Milky Way galaxy, the solar system, or even the Earth itself retain their structure. The expansion truly reveals itself only across the immense voids between galaxies. What drives this process? Scientists now believe the main culprit is dark energy, a mysterious form of energy that seems to exist within the very fabric of space. We do not yet know exactly what it is, but observations suggest that it causes the universe to expand faster over time, as if the cosmic balloon is not only inflating but accelerating with every breath. All of this leads us to a rather strange picture. We live in a space that may be curved, possibly finite yet without edges, expanding without any center. The rules governing it sometimes contradict everyday intuition, yet they fit together perfectly within the grand choreography of the cosmos. A simple balloon can help us imagine all of this: curvature, expansion, and the possibility that a long enough journey through space might bring you back to where you began. A small metaphor drifting through our thoughts, whispering about a universe that is not expanding into something else, but growing from within itself. The next time you see a balloon floating into the sky, try smiling at it. Within that gentle object hides a far greater idea: the shape of space, invisible curves, and the possibility that the final destination of a cosmic journey might also be where it began. And then a larger question appears: is the universe infinite? The word infinite carries a strange feeling of its own. It brings to mind endless regions of space stretching forever, chains of galaxies without end, and mathematical problems that make many high school students want to close their textbooks immediately. But when we ask the question seriously, science must begin with what we know. Current observations of the large-scale structure of the universe, especially from the cosmic microwave background, suggest that space has a geometry extremely close to flat, and within the framework of general relativity, a perfectly flat universe could indeed extend infinitely. If it is not truly infinite, then it is at least far larger than the portion we can observe. The part we can see is called the observable universe, a cosmic bubble about 93 billion light-years across. It represents the region of space from which light has had enough time to reach us since the universe began. But beyond that bubble, the universe may continue to stretch outward. There could be other galaxies, other enormous structures, perhaps even regions of space whose light will never reach Earth. The difficulty is this: we cannot prove whether the universe is infinite or not. Our view is limited, much like ants standing on a beach and looking around to see sand stretching to the horizon. The beach might extend across an entire continent, or it might end just beyond a few more dunes, where the tide forms a small pool filled with curious crabs. The ants simply cannot see far enough to know. And that is also our situation in the universe. In science, infinity is not a number you measure with a ruler. It is an idea, a possibility. And ideas like that cannot be observed directly. They can only be inferred from the subtle clues hidden in the structure of space. So far, when we look out in every direction across the universe, there is no sign of a final wall. There is no edge of space, no cosmic cliff where the stars suddenly stop, and no floating sign that reads, "Beyond this point, entry forbidden." But not seeing an edge does not mean that one does not exist. It may simply lie too far away, beyond the limits of what light can carry to us. As long as we remain bound by the speed of light and the expansion of the universe, humanity's field of view will remain just a small bubble within the ocean of space. If the universe is truly infinite, the consequences are astonishing. An infinite space could contain an almost limitless amount of matter, countless stars burning across the darkness, countless planets orbiting them, and endless clouds of dust and ice drifting between galaxies. Within that immense repetition, it is not impossible that somewhere there exists another planet resembling Earth. Perhaps there are forests there that grow sideways instead of upright, or oceans glowing with strange colors. Perhaps on such a distant world, other beings are also gazing up at their sky, asking the very same question: does space ever come to an end? Then the idea begins to feel slightly dizzying. If the universe is infinite and matter is distributed somewhat evenly, then certain arrangements of matter must eventually repeat. That means that somewhere unimaginably far away, there might exist another version of you, perhaps almost identical, or perhaps differing only in a small detail, such as choosing a different cereal for breakfast this morning, and that tiny change quietly altering the course of their day. Of course, this is not a scenario you need to worry about. Those regions of space lie at distances beyond comprehension. Light from there would never reach us, even if we waited longer than the age of the universe multiplied by every grain of sand on Earth. Yet the idea stretches the mind in a remarkable way. Infinity is not simply very large, it is the complete disappearance of boundaries. The cosmic map would have no final edge, only more maps, extending endlessly. Even so, science remains cautious with such conclusions. We have only one finite sample of data to study, the observable universe. Space might truly be infinite, but it might also simply be extremely large. So large that we have not yet detected the gentle curvature that could reveal its true shape. It might curve through higher dimensions, or form a strange geometric structure that we still lack enough data to imagine. Beyond space, there is also the factor of time. The universe might stretch infinitely through space, while still having a beginning in history. We call that moment the Big Bang. The idea of a beginning to the universe is itself mysterious, but it reminds us that no matter how vast space may be, the universe has not always existed in the form we see today. In philosophy, infinity has always been a difficult concept to grasp. Most things in life have limits: our time, our energy, even the number of cookies in a jar. Infinity breaks that pattern. It opens a boundless field of possibilities, both fascinating and overwhelming. Not everyone throughout history has been comfortable with this idea. Aristotle believed the universe must be finite, because a true infinity seemed too strange to exist in the real world. Even today, scientists and philosophers continue to debate whether infinity can exist physically, or whether it is merely a useful mathematical concept. But whatever the final answer may be, reflecting on infinity has its own value. It stretches our imagination and reminds us to be humble before the scale of the cosmos. When you look up at the night sky, what you see is only a local glow, a few lit windows in an enormous cosmic castle. And from a small planet orbiting an ordinary star, humanity continues to ask, how much farther does space go? We build telescopes to chase ancient light. We invent mathematics to describe things that are almost impossible to imagine. And sometimes, on quiet nights, we lie awake, wondering what lies beyond the most distant star our eyes can see. Perhaps the universe is infinite, perhaps it is not. But either way, what we have already learned about it is wondrous enough. The sheer scale of the universe alone is enough to nourish human curiosity for centuries. It is vast enough for science, for stories, for dreams, and large enough to remind us that we are only a small part of a much greater picture. In truth, you do not need to know how far the universe extends in order to feel that you belong to it. You are already a thread woven into its fabric, a small spark of thought appearing at the edge of the region of the universe we are able to observe. And yet the human mind is especially drawn to a familiar idea: boundaries. In everyday life, almost everything seems to have an ending. Walls, fences, sidewalks, lunchboxes, they all stop somewhere. So when we think about the universe, we naturally imagine that space must also have some final edge. Somewhere very far away, perhaps there is the ultimate end of space, like the last room in a vast castle, or the edge of a giant table hanging above an endless abyss. But it turns out that space does not need an edge. Something can be completely finite while still having no boundary. To understand this, let us return to a familiar example: the surface of the Earth. If you travel in a straight line in any direction, you will never fall off the planet. Nor will you encounter a sign that says, "End of Earth, please turn back." Instead, if you continue long enough, you will eventually return to the place where you began. The surface of our planet is finite, yet it has no edge. It closes perfectly back onto itself. Now imagine the same thing happening in 3 dimensions of space. You live inside a space that can connect back onto itself, just like the surface of the Earth, except that this happens within a 3-dimensional volume. If you could travel perfectly straight through such a space, after an incredibly long journey, you might return to your starting point without ever encountering a wall, a barrier, or any edge of the universe. In cosmology, this model is entirely valid. It is called a finite but unbounded space. It may sound like a paradox, but its geometry becomes quite clear once we find the right image to visualize it. A classic example is the torus, which looks like a donut. Its surface has no edge. You can move around it in different directions without ever leaving the surface. If you were an ant living on that donut, you could wander forever without encountering a boundary. All paths eventually reconnect with themselves. In a three-dimensional version of this geometry, space might behave similarly, a closed structure in which every direction links together through enormous loops. Another familiar analogy comes from classic video games. In games like Pac-Man or Asteroids, when a character exits the screen on the left side, it immediately appears on the right. There is no hidden tunnel. The map simply connects back onto itself. In theoretical cosmology, this idea is more than just a playful metaphor. Some models suggest that space could have a closed topology, where different directions connect in subtle ways. If that were true, in principle we might detect it by searching for repeating patterns in the cosmic microwave background, the ancient light left over from the Big Bang. So far, observations have not found clear evidence of such repeating patterns, but the possibility has not been completely ruled out. More important is the shift in how we think about space. Space does not necessarily sit inside something larger. There is no familiar outside of the universe. Space is not an object placed within a bigger container. It is the overall structure of everything that exists. Even if the universe is infinite, it does not need a final edge, because infinity is not a place. It is simply a property. Like numbers, you do not need to find a last number to understand that the sequence never ends. And in the same way, you do not need to discover the edge of the universe to realize that perhaps there is no edge at all. The idea of an edge of the universe feels familiar because it mirrors the way we experience the world. Almost everything in daily life has boundaries, walls, fences, coastlines, the edge of a table, so it seems natural to imagine that somewhere, very far away, space itself must also come to an end. But the moment we ask that question, a paradox immediately appears. If the universe has an edge, what lies beyond it? If there is still space outside, then clearly the universe has not truly ended. And if there is truly nothing there, then how could such an edge exist at all? A boundary with nothing beyond it to define it. For this reason, many cosmological models simply abandon the idea of an edge altogether. In those models, space has no boundary. You could keep traveling forever, or perhaps even loop back around without ever encountering a cosmic wall. The human mind tends to think in boxes. Everything has a beginning, a middle, and an end. But the universe seems largely indifferent to the tidy compartments of our imagination. It bends, it expands, and it may even repeat itself in subtle ways without ever leaving a visible outline. Yet this does not mean that everything is infinite in every direction. Space may have no edge, but time itself appears to have a beginning. About 13.8 billion years ago, the universe entered the phase we call the Big Bang, not a point in space, but a moment in history when space itself began expanding from an earlier, hotter, denser state. Asking what happened before the Big Bang can sometimes feel like asking what lies north of the North Pole. It is not exactly a meaningless question, but the familiar coordinates we rely on simply stop applying. Rather than a giant box whose lid we might one day lift and peer inside, the universe may be more like a melody being played, a piece of music unfolding through time and space, weaving through dimensions without requiring a final note. No edge, only curves and connections. So, if you have ever imagined a brave spacecraft flying to the edge of the universe, try picturing something different. A long and quiet journey where the horizon ahead is not a cliff, but simply more stars, more questions, and more space. If we turn the clock even further back before galaxies formed, before the first stars ignited, the universe looked very different. There were no planets, no stable atoms, only a soft glow filling all of space, like a warm mist spread evenly across the cosmos. That light still exists today. We call it the cosmic microwave background, or CMB. It is not just ancient light, it is the oldest light anyone can possibly see, a whisper from the universe's earliest times still drifting through space. To understand where this light comes from, we must return to the era shortly after the Big Bang. Back then, the universe was incredibly hot and dense, filled with energy and particles moving chaotically. Space expanded rapidly, and as it grew larger, the temperature slowly began to fall. For the first few 100,000 years, the universe resembled a turbulent ocean of particles and radiation. Photons, particles of light, could not travel very far because they constantly collided with free electrons and protons. Light scattered in every direction, much like trying to shine a flashlight through a thick fog. But then, about 380,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine, forming the first neutral hydrogen atoms. This event is called recombination. That moment changed everything. As the number of charged particles decreased, light was no longer scattered constantly. The cosmic fog gradually cleared. Space became transparent, and for the first time light could travel freely across the universe. The photons released at that moment are still flying through space today. That ancient light is still here. It spreads across the universe in every direction, quietly drifting through space for billions of years. In the beginning, it was a blazing flood of energy, fierce like the ultraviolet glow of a newborn universe. But as space slowly expanded and cooled, the light stretched along with it, softening into a faint microwave signal. From the roar of creation, it became a whisper, and that whisper is still around us. Right now, those ancient photons are passing through the earth, through the sky, through the walls of buildings, and even the room where you are sitting. They are like an invisible breeze blowing from the dawn of time. We discovered this light almost by accident. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were using a giant horn-shaped antenna to study radio signals from space. But no matter where they pointed the antenna, a strange background noise kept appearing. They checked their equipment, they reviewed their calculations, they even cleaned out a nest of pigeons living inside the antenna, just in case that was causing the interference. But the signal never disappeared. It was steady, persistent, and seemed to come from every direction in the universe. What they had accidentally detected was the echo of the Big Bang. It was the cosmic microwave background, or CMB, a phenomenon physicists had predicted but had never directly observed. The faint hiss in their radio signal turned out to be a doorway into the infant universe. Since then, scientists have mapped this ancient light in extraordinary detail. Space missions such as COBE, WMAP, and later Planck have captured increasingly precise portraits of the CMB. It is not just a faint glow, it is the blueprint of the universe. The CMB shows us the universe when it was only about 380,000 years old, an incredibly early moment in its 13.8 billion year history. At first glance, the image looks almost perfectly uniform, the same temperature and brightness in every direction. But when scientists magnify it, subtle details begin to emerge. Slightly warmer regions, slightly cooler regions, differences of only a few millionths of a degree. These tiny ripples were the original seeds of the universe. From those minuscule variations in density, gravity gradually gathered matter together over billions of years, forming stars, galaxies, and eventually every large structure we see today. In other words, those tiny specks on the CMB map mark the starting points of everything. They reveal how matter was distributed in the early universe. They allow scientists to test theories about the first moments of space and time. And even the shape of the universe leaves its imprint within this ancient light. If space is curved, flat, or shaped by a different geometry, the light of the CMB carries subtle distortions reflecting that structure. By analyzing the size and distribution of these tiny fluctuations, scientists can infer the geometry of the entire universe. So far, all the evidence points toward a remarkable conclusion. Our universe appears to be nearly flat, Much like studying ripples on a lake to guess the shape of the shoreline, scientists read the ripples in the CMB to understand the environment through which this light has traveled. Within that light lies data. Within each photon lies memory. There is something gentle about thinking of the CMB this way, not as a violent flame, but as a soft layer of ancient light spread across space. We cannot see it with our eyes, yet it is always there like a cosmic lullaby still playing billions of years later. If you had a radio sensitive enough, you could hear it everywhere, not as a clear melody, but as a warm background hiss, a faint static woven into the very fabric of space. It is like the baby picture of the universe, the first moment when everything became clear. That light has traveled unimaginable distances, survived the birth and death of countless stars, passed through spinning galaxies, and finally arrived here in your era. In a universe full of mysteries, the CMB is one of the rare things we can measure, map, and truly understand. It reminds us that to understand the origin of the universe, we do not necessarily have to search for the edge of space, because the answer has always been drifting quietly around us, waiting to be heard in that ancient light. So the next time you look up at the night sky, try to imagine that the dark emptiness above you is not truly empty. It is still filled with the light of the universe's dawn, too faint for our eyes to see, yet still there, telling the story of the beginning. The ancient light of the universe continues its journey. More than 13 billion years have passed, and each photon has been stretched by the expansion of space, carrying within it the quiet story of everything that has ever existed. Even now, in the near-perfect stillness of the cosmos, that light continues to travel outward, and so the question of a cosmic edge inevitably returns. Could there be, somewhere out there, a final boundary, a curtain of the universe where space suddenly stops? Not only in the pages of science fiction, but even in discussions held beside chalkboards and telescopes, this question continues to be whispered. Most modern cosmological models lean toward a rather simple conclusion. The universe probably has no clear boundary, yet in the dimmer corners of theoretical physics, a few more daring ideas still exist, possibilities in which certain kinds of edges might exist, even if we cannot directly perceive them. One of the strangest ideas comes from brain cosmology, a branch of string theory. In this picture, our universe is not the entirety of reality, but merely a three-dimensional membrane, a brain floating within a much larger space of higher dimensions. Everything familiar to us, particles of matter, electromagnetism, and the nuclear forces would be confined to this membrane, like insects trapped on the surface of a soap bubble. Only gravity appears more flexible, capable of leaking into other dimensions. Some physicists suggest that this could explain why gravity is so much weaker than the other fundamental forces. If that picture were correct, our universe might possess boundaries in dimensions that we cannot perceive. From our perspective, everything appears continuous and without edges. But to a hypothetical being living in 5 dimensions, with senses capable of seeing through those extra directions, our universe might look like a gigantic disk with an edge around it. The idea is both a little unsettling and strangely fascinating. If someone were observing from a higher dimension, it might be us who appear peculiar to them. Another possibility arises from the concept of cosmic domain walls. These are boundaries that might form when the early universe underwent phase transitions, somewhat like water freezing into ice, except that different regions might freeze in slightly different ways. In this scenario, different regions of space could settle into slightly different physical configurations. The boundaries between these regions would form enormous structures known as domain walls, separating areas where the laws of physics vary subtly. Many models suggest that such walls would have quickly disappeared during the evolution of the universe. But some speculative scenarios propose that they might still exist somewhere in the deep cosmos, like silent gatekeepers between different regions of reality. If you were to cross such a boundary, you might notice nothing unusual at all. Or perhaps you would suddenly find yourself in a region of the universe where chemistry behaves slightly differently. Maybe your atoms would remain stable, but your cup of tea would mysteriously taste a little more like lemon. Another idea imagines the universe as a bubble, not metaphorically, but literally in a physical sense. During the era of cosmic inflation, quantum fluctuations may have created bubbles of space. When inflation ended in one region, a bubble universe formed, each with its own set of physical constants. This scenario is known as eternal inflation. In it, space may resemble an immense cosmic foam, where each bubble represents a separate universe, potentially with different gravitational strengths, numbers of dimensions, or other physical laws. In that picture, boundaries exist where our bubble universe touches the surrounding inflating space, or where two bubble universes collide. Yet those bubbles might lie so far apart that such encounters may never occur. There is a strange beauty in this idea, how a universe might be just one bubble in a vast ocean of cosmic foam. Another equally peculiar model comes from the logician Kurt Gödel. In 1949, he discovered a solution to Einstein's equations describing a universe that rotates as a whole, not merely galaxies spinning individually, but space-time itself twisting like an enormous cosmic vortex. In such a universe, the curvature of space-time could form closed loops that would allow you to travel along a special path and arrive back in your own past. Not a wall at the edge of the universe, but a different kind of boundary altogether, the boundary between cause and effect. However, despite its mathematical elegance, Gödel's rotating universe does not match what we observe. There is no evidence that the entire universe is rotating in that way, and the time loops allowed by the model remain confined to theoretical physics. Still, these ideas remind us that the universe may be far more complex than humanity once imagined. And sometimes, even when we fail to find the edge of space, we may still encounter other strange boundaries, places where geometry, physics, and imagination meet. Some models in physics are not created to describe the world exactly as we see it before our eyes. Their value lies elsewhere in their ability to stretch our imagination, forcing the mind to step outside familiar patterns. The equations of the universe were not written to match human intuition, and sometimes those equations open doors to possibilities so strange they almost sound like science fiction. One such idea is the holographic principle, not the shimmering three-dimensional images from movies. Here, it is a deeply serious mathematical concept. Everything that happens within our three-dimensional space could be encoded on a distant two-dimensional surface, much like how a flat hologram can contain the information of an entire three-dimensional image. In this view, the boundary of the universe is not a wall or an edge of space. It may instead be the place where the fundamental information of reality is stored. This idea emerged from studies of string theory and the thermodynamics of black holes. So far it remains speculative, but its elegance and power make it difficult for many physicists to ignore. The important point is not that we will someday encounter a wall at the end of the universe, or a gate with a sign reading, "End of space, do not cross." The deeper message of these theories is this: if boundaries exist, they may exist in forms completely different from what we are used to imagining. An edge of the universe might be a change in the geometry of space, or an initial condition of the cosmos, or even the limit of information and the laws of physics themselves. Some boundaries are not walls, they are the limits of what we can know. And in a sense, that too is a kind of boundary. Human beings evolved in rooms, on continents with coastlines, in a world where everything seems to end somewhere. So when we step into cosmology, we carry with us the instinct to search for final edges. But the universe never promised to behave according to our intuition. Perhaps it quietly loops back on itself. Perhaps it stretches endlessly in every direction. Perhaps it lies upon the surface of a higher dimensional structure we cannot perceive. Or perhaps its true shape is something the human mind has not yet imagined, a structure bending, connecting, and folding in ways our language has only begun to describe. And whatever the answer may be, we are still drifting within that mystery. There is a strangely peaceful feeling in the thought that the universe might have no ending point, not only infinite in size, but infinite in what remains unknown. Perhaps even our questions extend forever. Simply understanding the universe we already observe is an immense task, billions of galaxies, deep swirling black holes, ancient background radiation, and space that may curve or expand forever. Yet from time to time, cosmologists like to stir things up with an even bigger question. What if this universe is not the only one? That is where we enter the idea known as the multiverse. According to this hypothesis, reality might not consist of just one universe, but many, perhaps infinitely many, universes with different physical laws, different particles, different histories. There might be places where gravity behaves in strange ways, or universes where tiny choices in daily life lead to entirely different timelines. However, one thing must be made clear. We currently have no direct evidence for other universes. No observation, no measurement, no signal waving across a dimensional fence. For now, the multiverse is an idea framework, not a conclusion. Still, the concept did not appear out of nowhere. One of the most widely discussed versions arises from cosmic inflation theory. In this model, the extremely rapid expansion of the early universe did not occur uniformly. Some regions stopped inflating earlier than others, forming separate bubbles of space. Each bubble becomes a universe. They may evolve independently, each with different natural constants. Some might be too strange for matter to exist at all. Others might contain structures entirely unlike anything we know. Our universe could simply be one bubble within that enormous cosmic foam. Another version emerges from quantum mechanics. In the many worlds interpretation, every time a quantum event has multiple possible outcomes, all of them occur but in different branches of the universe. In one branch, you wake up early. In another, you hit the snooze button. In some distant branch, perhaps you accidentally invent teleportation while trying to make pancakes. Each possibility becomes its own reality. This is not merely playful speculation. It is a serious interpretation of quantum mechanics designed to avoid the concept of wave function collapse. But like other multiverse ideas, it remains beyond our ability to directly test. And so it remains in a familiar place within cosmology, somewhere between science and the wonder of imagination. Occasionally, I like to imagine that somewhere out there, in another branch of reality, there's a version of us living a completely different life. Maybe in one universe, you're a famous harmonica artist. In another, you're standing on a TED stage, giving a talk about strange mustache choices and how they change the course of your timeline. It sounds funny, but if the multiverse exists with countless branches of reality, then almost every possibility might happen somewhere. The only catch is that we can't step into those other branches. There's no inter-universal train station, no train that takes us to another version of our own life. Some scientists have taken this idea even further. Cosmologist Max Tegmark once proposed that every consistent mathematical structure might exist as a physical reality. In other words, if something can exist in mathematics, then somewhere it could exist as a real universe. This opens the door to worlds with completely different rules. There might be universes where the fundamental particles are not the same as ours, where the value of pi is not what we know it to be, or where time does not flow in a straight line, but twists into some strange kind of motion. It's a bold idea, almost mystical in tone, and because of that, it's also controversial. One of the biggest questions is, how could we test such a thing? If other universes lie beyond any signal we could ever reach, how could we study them? Science usually advances by testing predictions, measuring results, and refining models. But when we talk about places that no signal can ever reach, the familiar tools of science start to feel powerless. Some physicists see the multiverse as a sign that our theories are being stretched too far beyond the realm of testability. Others see it as a reasonable explanation for our own existence. If there are countless universes, each with different constants and laws, then it's not so surprising that we find ourselves in one that allows life. It's a bit like a casino with infinitely many dice tables. Most tables produce nothing remarkable, but at one of them, the numbers fall just the right way, and we simply happen to be sitting at that table. Some cosmological models even suggest that the multiverse might leave indirect traces, for example, unusual patterns in the cosmic microwave background, that could be caused by collisions between bubble universes. So far, we haven't found anything like that. But physicists tend to keep an open mind. In the history of science, many strange ideas eventually became major discoveries once we finally had the tools to test them. Whether other universes exist or not, thinking about them has a special effect. It forces our imagination to stretch. It reminds us that reality might be far larger, stranger, and richer than we once thought. And then the original question appears again. Where does space end? At first, it sounds like a simple question, the kind a child might ask while looking up at the sky and wondering whether the heavens have an edge. But the more we study it, the more we realize that space isn't like anything familiar. It's not a room with walls. It's not a road with a stopping point. Space could be finite and still have no boundary. It might curve, bend, even connect back to itself in ways our imagination is only beginning to grasp. And even stranger, it's expanding. Galaxies seem to move away from us at enormous speeds, not because they're racing through space, but because the space between us and them is stretching over time. Yet our ability to observe the universe still has limits. There is a cosmic horizon, a boundary beyond which light hasn't had enough time to reach us since the beginning of the universe. Beyond that edge of visibility, we simply don't know what exists. Maybe the universe extends forever. Maybe it curves back on itself, forming an enormous loop we would never notice. Maybe our universe is just a tiny bubble, drifting in a vast, higher-dimensional ocean. Or maybe the multiverse is simply a beautiful idea that can never be tested. Either way, one thing we know for certain is that space is not empty. It's filled with delicate structure and subtle energy. It carries the light of ancient stars and the faint echoes left behind by the Big Bang. It has no center, and according to everything we observe today, there is no sign of an end. Still, many questions remain. Is the universe truly infinite, or just unimaginably vast? Is its geometry flat, curved, or something else entirely? And if there really were an edge of space, what would lie beyond it? We may never find all the answers, but that isn't a failure of science. In fact, the unanswered questions are exactly what drive science forward. Every photon we collect, every map of the cosmos we draw, every model we refine brings us a little closer, even if the destination keeps shifting like the stars themselves. Perhaps space never truly ends, not necessarily because it is infinite in size, but because its mystery seems endless. And when we sit here quietly thinking about everything that lies beyond the boundaries of our knowledge, that very moment is already a small miracle of the universe. Perhaps the greatest gift that space offers us is not the distant stars or the vast silence of the night sky. Something even more precious lies elsewhere in its ability to make us ask questions. From the moment humans first lifted their eyes toward the sky, the universe opened a space large enough to hold the greatest questions the mind could imagine. Space is not only the place where galaxies drift past one another in the darkness, it is also the place where our curiosity is allowed to travel the farthest. And perhaps that is why the idea of an endless universe feels strangely fitting. Not only because the distances between galaxies are so immense, but because the questions it awakens seem to have no final boundary. Perhaps space never truly ends, because our questions do not either.